Hello, I am David W. Parker. This is Programming Today. I learned 3D Math Series, episode 18. We're going to be looking at types of transformations, and not just linear ones, all types today, and just some facts about each types of transformation we'll be looking at. So let's start with some linear transformations. A linear transformation is linear if addition and multiplication by a scalar is preserved after the transformation. So addition would be f of a plus b is equal to f of a plus f of b, and f of ka is equal to k of f of a for multiplication. So to prove that those hold, you can see we have f of a is equal to am when m is a square is linear, and you can see that by f of a plus b is a plus b m, which is a of m plus b of m, which is f of a plus f of b. Additionally, if f of ka is equal to ka times m, which is, because of association, k of am, which is k of fa. So therefore, square matrices end up being linear transformations when they are scaled. If a linear transformation with a transform will transform the zero vector into the zero vector. So f of 0 is equal to a, and a is not equal to 0, then f is not linear because f of k of 0 is equal to a when it should be equal to 0. So f of k of 0 is not equal to k of f of 0. So translation, this would be like a translation, would not be a linear transformation. Next up we have affine transformations. They are a linear transformation followed by a translation. Any linear translation is an affine, but not all affine translations are linear. That's because of the translation as well. All transformations from episodes up to now are or have been affine transformations. And they take on the form v prime is equal to v times the matrix plus b, and the plus b is the translation portion. Invertible matrix is if there's a way to undo the original matrix transformation, then it's invertible. So if we have this new function f of -1, and you multiply it times f of a, and it's equal to a for all a, then it is a invertible transformation. All transformations we've done so far, except for projection, can be undone. Think about if we have a 3D matrix and we convert that to a 2D matrix, thus transforming it with a projection, we obviously lose the extra data, and that cannot be undone. That's why projections are not invertible transformations. If a matrix is singular and has no inverse, then it is also non-invertible. Angle-preserving transformations is if the angle between two vectors is not changed in magnitude or direction after the transformation. Only translation, rotation, and uniform scaling transformations are angle-preserving. Reflection isn't considered because the direction of the angle may be inverted. Orthogonal transformations we'll be looking at a little bit more later, but on the short version right now, the axes remain perpendicular and no scalars are applied. Translation, rotation, and reflection are the only orthogonal transforms. Length, area, angle, and volume are preserved. The determinant is plus or minus 1, and it's affine and invertible. Rigid body transformations are the location and orientation, but not the shape if it changed. Angle, length, areas, volumes are preserved. Reflection is not a rigid body transformation. And proper transformations are orthogonal, angle-preserving, invertible, and affine. Determinant of a rotation matrix is 1. And in summary, we have this chart here. You can take a look at the transform at the top, and you can see each of the transformations on the bottom, and we can basically see if a linear transformation is always linear and it's always an affine, but it's not necessarily invertible, angle-preserving, orthogonal. It's rigid body length preserved, area volumes preserved, or determinant. Just because these have no value here doesn't mean it's never. It just means it may not be the case. Affine transformation is not always linear, but it is always, of course, an affine. And the determinant is not equal to 0. Invertible is always invertible. Angle-preserving transformations are always an affine. They're always invertible, and they're always angle-preserving. But they're not necessarily linear, orthogonal, rigid, etc. Orthogonal transformations are always an affine and invertible, and orthogonal, and plus or minus 1 in the determinant. Rigid body transformations are not always linear, but they are all of the rest of the things, and have their determinant as 1. Same thing with translations. They're not necessarily linear, but they are all the rest of the things. Rotation is everything. They're always angle preserving, orthogonal, rigid, etc., etc. Uniform scaling is always linear, affine, invertible, and angle preserving, with a determinant of k to the power of n. Non-uniform scalars are linear, affine, and invertible. Orthogonal projections are orthographic projections, are linear and affine, the determinant of 0. Reflections are linear, affine, invertible. Orthogonal, length and volume and area are preserved and determinant of -1. And shearing is linear, affine, invertible, and area is preserved and determinant of 1. That's it for this episode. If you like what you saw, go ahead and give a like and a subscription. Go to ProgrammingTIL.com and sign up for my newsletter. We'll be looking at more matrix math and different math equations that we need to know for matrices moving forward. Thanks, and have a great one.